So welcome to our official start of data structures today. Our plan for today is to finish up the discussion of the AVL tree. So I'll go ahead and start sharing my screen. And as a reminder, so the AVL tree is this special type of binary search tree. So every AVL tree is a binary search tree, but not every binary search tree is an AVL tree. And the purpose of the AVL tree was that it added this extra invariant called the Avl invariant related to the balance factor. The balance factor is this formula right here, where it's the height of the left subtree minus the height of the right subtree. And what the AVL tree invariant says is that every balance factor of every node must be either -1, 0, or 1. The purpose of this invariant is to guarantee that the height of our tree is going to be upper bounded by log n, O of log n. And this is good because we said last time that all of our runtime functions, find, insert, delete, the runtime of those functions is determined by the height of the tree. And in fact, it's going to be the same as the height of the tree. So the fact that the height of our tree is O of log n guarantees that we're going to have log n efficient operations. So that's again, the main point of why we're talking about the AVL tree. And again, these balanced search trees, they form the foundation of really everything interesting that happens in computer science. Every time you go onto Google and do a Google search, there's a balanced search tree in the background handling your query, making it go efficiently. Every time you're logging onto GitHub and log in your username and password, there's a balanced search tree inside of GitHub that stores all that information. Every web page you interact with, it's balanced trees that's doing this. They're not always AVL trees. We said last time that there's a whole bunch of different variants, but we chose the AVL tree in this class, a very common one for data structures class because it's particularly simple. So there's, switch over to, here we go, the notes that we're doing. Again, here's an example of a balanced tree on the left and an unbalanced tree on the right. And our goal is to keep our trees as close to this shape as possible. In order to do that, we started talking about this idea of tree rotations. The big picture idea of how we're going to do our insert function with the AVL tree is we're first going to insert just like we did with the binary search tree. Then we're going to find all of the nodes that have violated our AVL constraint and do one of these rotations on them. So we started talking about these rotations last time. We saw the mechanics of how to do the rotations, but we haven't yet talked about the when and the why of the rotations. We've just talked about the what and the how. And so today we'll quickly review what are these rotations, and then we will talk about the when to do them. And that'll be the really key important thing to take away from today's class is the sort of the background algorithm, the idea of when to do these rotations. Again, the textbook has really good, I think, explanation of this. And so after we go through the notes here, I will point you over to the textbook, show you like the key paragraphs to read and to have up while you're doing your actual coding assignment for this homework. So there's two rotation strategies, a left rotation and a right rotation. And this is sort of the key example to keep in mind of the left rotation, that when you have a tree ABC like this, we always, when we're doing a rotation, we specify the two nodes that are being rotated on. So A and B in this case, A and B are rotating. And in a left rotation, we're taking all of the nodes and moving them to the left. So the A comes down, the B comes up, and the C comes up, and we get this over here. The really interesting property of a left rotation is that these balance factors, I have them drawn here in orange, these balance factors are going to increase. So when we had the balance factor of -2 right here, it's no longer going to be -2, and it's going to go up. And we said that this balance factor is always going to be, after you do a rotation, it's always going to be a number 0, 1, or 2. I think I have that written out formally right down here. So if you do a balance factor on a node D that used to be -2, and you do one of these left rotations, then the new balance factor must be either 0, 1, or 2. And the importance of this property is that it means that if we do this balance factor, we're guaranteed that nothing bad is going to happen. We're never going to get into a worse situation where the balance factor suddenly becomes 3 or 4 or something really big like that. The balance factor is either going to, in magnitude, stay the same, or it's going to go down. Yeah, so this is the key picture that I sort of remember in my head about the balance, about the left rotation, what it's doing. But this right here is actually the formal definition. And this is the picture that you'll see in the textbook and on Wikipedia, if you look on Wikipedia. And so the nodes and circles, those are the key nodes that you're actually doing the left rotation on. So here in this case, it's D and F that I'm rotating. And then these nodes and triangles, the triangle just is meant to be indicative to you that it's an entire tree down there, not just a single node. So when we do this rotation, this A subtree stays attached to D as its left child, and it's the entire A subtree, not just the A node by itself. The A and the G ones, the ones on the wings, those are the sort of the easiest ones. They just stay exactly the same. It's this one in the middle, E, that switches from being a left subchild of F to a right subchild of D. And when it does that, it maintains the binary search invariant of that. Here, recall that the binary search invariant is that all nodes to the right of D must be greater than or equal to D. And so in particular, everything in E must be greater than or equal to D because it's to the right of D over here. And over here, it stays to the right of D. Similarly, because E is to the left of F, it must be less than or equal to F, and it stays to the left of F over here. This will be one of those concepts that seems like really intuitive looking at it in pictures, but when you get into the code, it'll be really easy to accidentally write code that does something different. And so you want to make sure that, especially for this middle node, that you're paying close attention to that. So that's the left rotation, and the right rotation is exactly the opposite, the inverse of that. That if we start down here is what we had at the end of the left rotation, and now we do a right rotation, we go back to what we had before. The right rotation moves the D up top and the F down below. Okay, let's do 2 more examples now of these rotations that will, I think, illustrate the purpose of the rotation, the when and the why of the rotation, and also help jog your memory a little bit more about the what of the rotation and the how, just getting some more practice with that. And so the example that I want to do, we're going to start with a valid binary search tree and also a valid AVL tree, VST/AVL tree. Satisfies both of these invariants. And what it looks like is F, G, C, D, and B. And we can go through and calculate the balance factors on these nodes. Again, so this is something that you want to be at the point where you can just look at a tree and just instantly get the balance factors out of it. When you get to doing the coding assignment, you're gonna, it'll just make the coding, like, it'll still be difficult, but it'll make it much, much easier if you can just look at an example tree and immediately tell whether it's a valid AVL tree or not, and exactly which nodes is breaking the condition. So if it's a leaf, it always has a balance factor of 0, and then it's left minus right. So size of the left is 1, size of the right is 1, so 1 minus 1 is 0. And then left minus right, size of the left. Again, the size is the height. So there's 2 levels here. There's 3 nodes, but there's 2 levels. So we use a 2 on the left, and then a 1 on the right. 2 minus 1 is 1. And so that's why it's a valid AVL tree and binary search tree. What I want to do next is add insert the node A. If we do that, that'll give us the tree F to G to C to D to B. So this is the original tree that we had before. I just copied it down. And now when we insert the A, we keep going to the left. It's less than everything. So it'll come down here. And this is where we add the A. And next, if we redraw all of these balance factors here, 0, 0, 0. Here we get 1 and 1. Now we get a balance factor of 2 here. And so we're not in the, we're no longer an AVL tree. And we're going to use a tree rotation in order to fix this. So in this case, our tree rotation will be a right rotation. Do a right rotation. And the two nodes that we're going to consider are the F node and the C node. We're going to be considering the F node because that's the one that is breaking the invariant right now. And so we want to reduce the balance factor of this node. And that's the point of the rotations, is to reduce the balance factors. And then we're doing the C node as well because when we did our insertion of A, we passed through the C node. So in order to get to A, we went down to C here, and that's why we're not choosing the right child of G, we're choosing the left child of C. We do this right rotation, C will come up to the top, and the left children of C will stay the same. That's a B, and then an A. The F will become a right child of C, like this, and the G stays as a right child of F. And then the tricky part is this right child of C, because C came up to the top and it has a new right child. D can't stay as the right child of C. It must now be the left child of the previous root node F. And so we get our D down here like this. And if we calculate all of our balance factors now, 0, 0, 0, 1, 0, 0, then everything is good and we are in the valid AVL tree. So not valid to the left, valid to the right, and we've fixed our breaking condition right here. Are there any questions about either this example or anything that we've talked about so far with the AVL trees? Okay. And we're going to do a second example right now. And the difference between these two examples is going to be like the key difference about inserting in the AVL tree and doing these rotations correctly. So we'll start with that same tree that we had before, F into G, C, D, B. So this part of the tree right here is exactly the same as this right here. The difference is now we're, instead of adding an A, we're going to add a B, or sorry, adding an E. And now when we add the E, so E is to the left of F, so we'll go down here. E is to the right of C this way, E is to the right of D, go this way, like so. And let's recompute our balance factors. So 0, 0, 0 for the leaves, a -1 for this D right here, a -1 for this C. These numbers are negative because we do the left minus the right, and they have right children, but no left child. And then a -2 up here, or sorry, a +2 up here for F. We have 3 height on the left-hand side and 1 height on the right-hand side. Again, this convention of the balance factor of doing the left side minus the right side is what the textbook uses, but if you look on Wikipedia or other sources, so Wikipedia in particular uses the right minus the left, and other sources, it's just arbitrary which one they use. So if you do look at other sources, then you'll have to just make sure that you're careful about the particular balance factor definition that they use. And what we're going to do now is we're going to do the same right rotation that we did before and see what happens. So we have this F node up here that's got a balance factor of 2, and we want to fix that balance factor, and so we're going to do the right rotation to do so. So again, right rotation, also on F and C. And what this will give us, so C will come to the top, B coming off the left child, and F coming off the right child, and G coming off the right child of F. And now this subtree right here, this DE subtree, can't stay as the right child of C, so it swaps to the left child of F, and we get D and E like this. Let's compute the balance factors again, and we get 0 and 0 and 0 and -1 and 1. And now up here we get -2. So again, it's the left minus the right. Left-hand side height is 1. Right-hand side height is 3. And so we have 1 minus 3 gives us -2. So in this case, when we did our right rotation, we did not, nothing good happened. We did not maintain our Avl invariant. We just went from a +2 balance factor to a -2 balance factor. So we didn't make things worse, we just didn't make things better. Are there any questions about why this is an invalid Avl tree, or how we did this rotation, or anything along those lines? Okay, so then our key observation is that sometimes doing this right rotation, so rotating on the 2, is good, sometimes it's not good. And what's the key difference that makes it good versus not good? Here, notice that the signs of these balance factors are the same. Both positive. Here, notice that the signs of the balance factor are different. We have positive here and negative here. So you're positive, and this one down here is negative. This is the particular situation where something bad happens. If the signs are the same, you're good. If the signs are different, you're bad. And by bad, I mean that you're not going to reduce your balance factor when you do the switch. In a sort of more advanced data structures class, so this would be something like, say, in a graduate level data structures class, what we would do is we would actually like formally prove that these are the conditions that cause things to work or not work on a rotation. I think at the thing that you should focus on at this point is not necessarily trying to be able to formally prove that this is the good case and this is the bad case, but be able to just sort of convince yourself with some examples that this is going to be a good case and this is going to be a bad case. So here I've done an example with a right rotations where the first number up here is a +2. And so my recommendation for you before starting your actual coding part of the homework is to try to generate some trees. I'll write this out too. Try to generate some trees where the balance factor of the root is 2 and the left child is either plus or minus 1. And just see with a couple of examples that doing a right rotation will work in this case and not work in this case. It'll be tempting to try to skip this, but then I think when you get into the actual coding, you'll have to be thinking about this and the coding, so it'll make the coding harder. So I strongly recommend doing this before starting coding. Similarly, do the opposite with a left rotation. Create a tree with root of -2 and right child is plus or minus 1. And you should be able to convince yourself that if root and child are both negative, then a left rotation will fix things. Fixes the balance factor. But if you have different signs, then the left rotation doesn't fix it. Are there any questions about this task right here and this principle of that if the signs are the same, a rotation fixes it. If the signs are different, the rotation doesn't fix it?
So would this be like a basic algorithm for determining whether or not to do a rotation then?
Exactly. We'll see that in our final algorithm for determining what to do. This will be like the first step. You check to see if the signs are the same. If they are, do a rotation, and you're good. Good question. Any other questions? Okay. So this begs the question then, what do we do when the signs are different? What's our solution? What to do when signs are different? And the answer is that we'll do a rotation to make the signs the same. So let's see what that's going to look like. I'm going to redraw the tree that we had above, the F, G, C, D, B tree, like this. So this is the tree before we've done an insertion. This is a valid AVL tree at this point. And we're going to insert the E again. So the E like this. And let's just redraw our balance factor numbers so that we can reference them. So we do left minus right, so -1, left minus right, 1 minus 2, -1, 3 minus 1 is 2. And so again, it's the C and the F balance factor that are different. And what we're going to do is we're going to do a rotation on CD, a left rotation on CD in order to change the balance factor of C so that it'll be non-negative. The reason I know that it's going to be CD that is the thing that we need to do about the rotation on is because when I was inserting the E node down here, I passed through both C and D. So F is the node that I'm ultimately trying to fix. It's got the 2, it's the one that breaks the Avl invariant, but it can't do it with a rotation yet because C is negative. And so I'll keep going down the path to D, rotate C and D, that'll make this node non-negative, and then we can do our previous right rotation.
Why does the fact that you pass through CD, like, is that just, it doesn't seem so obvious to me that you would do it on CD just because you pass through it.
Yeah, it's a great question. So first of all, it's definitely not an obvious thing. So if it doesn't seem obvious, then you're in good company. It shouldn't be obvious because it's not obvious. Let's see, so this is one of those sorts of things that we could like formally prove, but at this point in your like programming careers, it's better just to try to get some intuition about this. So I'll try to do the intuition rather than the formal proof. And the first thing about the intuition is that when you do an insertion, the only nodes whose balance factors will change are the ancestors of the node that you inserted. So here, when I inserted the E, I changed the balance factor of the D, the C, and the F, but I didn't change the balance factor of the B or the G. So the fact that both of these nodes have changed balance factors is one of the things that makes this seem like a good thing to do. Another property of our rotations is that a right rotation, so let's say I was going to rotate B and C, a right rotation is going to lower the balance factor of my new tree. So if I start at -1, by doing a right rotation, I'm going to make it go more negative. And that's the opposite of what I want. I want to make this not negative. And the left rotation has the property of increasing the balance factor. And so that's those two principles combined are the sort of I guess the intuition for why to rotate C and D. There's another one of those things though, that you just have to do a lot of examples to sort of convince yourself that that's true. Great question. Any other questions so far? Okay, so yeah.
So to get the signs to, is it always going to be like, for example, like we're originally trying to do a right rotation, and to fix the signs, we're always going to do the opposite, like to do a left rotation. Is it always going to be opposite, or would you ever like start with a right rotation, but then you see like the signs are different, and do another right rotation to fix the signs?
That will be another property that we'll see, is that it's if you first do a right, then you're going to do a left, or if you first do a left, then you're going to do it right. Yeah. That's a good thing to keep in mind when doing your code. After working through these examples, what I'll do is I'm actually going to switch my screen over to the textbook, and we'll look at the section of code that does this in the textbook, and that'll be really close to what your final implementation will be like. It'll walk through the steps of here are the 4 cases of what to do. And we'll see that, yeah, if you first do a right, then you have to do a left afterwards, and vice versa. Great questions so far. Any other questions? Okay, so let's do this left rotation on C and D. And So the D will come up to the C. There's another good example because I think this is the first example we've done where it's not the root that we're rotating. You don't have to only rotate on the root. You can rotate on anywhere in the tree. So D comes up, C comes down. E stays as the right child of C. And now B is the left child of C, like this. So this is the result of just rotating this subtree right here. Everything that's off of the subtree, not involved in the rotation, stays the same. So the F and the G stay the same up here. And now when we go through and I'm going to label all of my balance factors, we get 0, 0, 0, left minus right, 1 minus 0 is 1, left minus right, 2 minus 1 is 1, and left minus right, 3 minus 1 is 2. And actually you can see that this is the same exact tree structure that we had before when I did the inserting of the A. Right here. The particular letters are different because I've inserted a different letter, but the actual shape of the tree and the numbers of the balance factor is the same. And so that tells us that if we now do that right rotation, then we'll be in a good place. So let's go ahead and do that. I'll do a down arrow here. Right rotation, and it's always whenever you have to do 2, the second rotation will always be on the node that's violating your constraint. So in this case, F, followed by the node that you just did a rotation on. So FD. And that causes the D to move up, the F to move down, G stays as a right child of F, C and B stay as left children of the D, and then this E will swap from being a right child of D to a left child of F, like that. And now we are, we're good. We calculate all our balance factors, 0, 0, 0, 1, 0. We're an AVL tree again, and that's what we wanted. So it'll turn out that when you do one of these insertions, if you have a positive 2, there's only 2 things that can happen. You either have to do a single right rotation if the signs match, or you have to do a left followed by a right if the signs don't match. If it's a negative 2, then it's just the inverse situation where you first do a left rotation. If they match, if they don't match, it's a right followed by a left. Don't try to copy that down exactly. As I said, it's really, there's a lot of like lefts and rights going on. So what I'm going to do next is switch over to the textbook, and we'll just see here what that looks like. So they have a function rebalance, and you can see that, so the node here is the node that violates the AVL constraint. So that has either a positive or a negative 2. They have a balance factor attribute for the node. They're checking to see whether it's less than 0 or greater than 0. In this case though, if something is less than 0, it must be negative 2. And if it's greater than 0, it must be 2. So that's something that they don't spell out explicitly in the code here, but it's just a property that we know about the situations that you were going to call this, because you would never call it on a node that has a 1, -1, or 0, because those already satisfy the conditions. And then here you can see that if the signs don't match, so less than, greater than, then first do a right, then do a left. Otherwise, if they do match, just do a left. Again, signs don't match, first do a left, then do a right. Otherwise, just do a right. So this is a really good piece of code to reference in your homework assignment while you're working. Are there any questions about this code or about the example that we just completed? Okay, then so that the formal or the full algorithm for doing an insertion then is you first do the BST insert. And then you walk along the path of nodes, the ancestors of the node that you inserted. So I'll write that as for each ancestor of the inserted node. If the balance factor is either -2 or 2, then call the rebalance function. I think the big picture idea of this is not too bad, but the actual like implementation of it is there's just a lot of subtle things that can go wrong, and so I'd say this is by far the most difficult function that you'll have to implement in this class. Some of the common mistakes that people make are, first of all, they only consider the first time that the balance factor is -2 or 2, and then they stop doing their recursion or their loop at that point. And so you only rebalance once. It's possible in one of these trees that you could have to rebalance many times though. Let's see. Yeah, so you just have to ensure that you're calling this multiple times. Another very subtle point is that how you're going to be doing the rebalancing for a root node is going to be different. The idea is going to be the same, but the actual code that you'll have to do is going to be different for a root node and for a child node. The reason for this is that in your AVL tree class, you'll be storing the root node. It's not a child of something else. It's just the self.node member variable attribute of the AVL tree. And so it's just going to need to have a separate case of situations because you assign that variable differently than you assign the child of another node. And so it's very common to get something working for either just the root node and not the children, or just the children and not the root node. And so that'll be one of the things that you want to pay close attention to in your test cases is it working on a child or a root, or is it not working on a child or not working on a root? Another like really common mistake that gets made, we switch over here. So you can see that here we're referencing rights and lefts kind of all over the place. And it's not just this rebalance function that's going to be referencing rights and lefts. It's going to be your insert function. It's going to be your rotation functions. There'll be like right and left children everywhere. And it'll be really tempting that after you get it, like I say, after you get the left rotation working, basically copy and paste the code for your right rotation and then switch the lefts and the rights. And that's what you should do. But it's really easy to miss one of those lefts and the rights and not really catch that. So you have to be really, really careful about if you have a case for for one side, making sure that the case for the other side is exactly the opposite. Very easy to make that mistake. Let's see, I'm going to switch over to the code next and actually talk about the code a little bit. So here I'm loaded up into the containers project in the AVL tree branch. And if we look at containers, here's my avltree.py file. So let's open that up. Again, I've been emphasizing this a lot, but I did not CD into the containers folder. I'm vimming into the relative path directly, like this. And there's, what we're gonna do now is I'll just kind of walk you through the order that you should think about implementing these functions and try to give you some tips on the implementation. So the first thing is this AVL tree class right here. I'm gonna go ahead and also open up at the same time. So I did :tab-E again to open up a new tab, and containers/binary tree. Oops, I want container/bst.py. And here is the syntax that I use to make the BST a subclass of binary tree. And the purpose of doing this, making BST a subclass of binary tree, is so that the BST gets access to all the member methods of binary tree. One of the ones that you'll need in this assignment is the height member method. In order to calculate the balance factor correctly, you need to have the height available to you. And what we're going to do, what you'll need to do, is to make the AVL tree a subclass of the BST. You want it to be a subclass of the BST because you want all of the functions inside both the BST and the binary tree. Because BST is already a subclass of binary search tree, we say that subclassing is transitive, meaning that because AVL tree will be a subclass of BST, it'll also be a subclass of binary tree. So in order to do that, you'll have to just modify the class statement right here. And you'll also have to modify the init function right here to call the constructor right here, the super constructor. You'll want to do this as well. So that'll be relatively quick thing to do. The next things that you'll want to work on is getting, let's see, so I've provided you some code to compute the balance factor. And one of the differences between the code in this assignment and the code in the textbook is that the textbook includes an attribute in the node object for the balance factor, but we're just going to compute it every time rather than storing it in an attribute. This doesn't actually affect the asymptotic complexity of your runtime, but it will add a slight constant factor. But it ends up simplifying the code a lot because you don't need to recompute this and track it every time. And I've already provided this for you, so you can just use this anytime you need to compute the balance factor of a node. The key one that you'll want to implement first, though, is this is AVL tree satisfied. Again, that's always, whenever you're starting a data structure, always get the invariants implemented as soon as you can because they're really useful in debugging. For the binary search tree invariant, you had to implement some other functions, the find largest and smallest functions, in order to do the binary search tree invariant. But there's no other functions that you have to implement for the AVL tree. The function that you need is this, the balance factor, which uses the height, and you'll get access to that because of the being a subclass of BST. The next things that you'll do is the left and the right rotate. And again, this there's code available for this in the textbook. I'm going to scroll up to the top here, and here they have code for the rotate left. The code for your rotate left will follow the same sort of patterns in here, but it'll have to be significantly different. The The reason for this is the way that they store their nodes internally, that their nodes have an explicit reference to their parent. So here you can see it does something like node.parent.leftChild. And so you can get access to your parent node once you're at your node. For our version of the AVL tree, however, the nodes do not have any explicit links to their parents. And so you'll have to be a little bit more careful when you're doing the rotate left in order to do that. What their rotate left does is it actually modifies the original tree. And what your rotate left should do is it will return a copy of a new tree that has the structure that you want it to have. So that's the difference between theirs and yours. And that's the key challenge for this function. Their function modifies the original tree in place. Your function should return a copy of a new tree that is the tree that you want as a result of the rotation.
Professor, is that the primary benefit of a static method?
Good question. Yeah, so let's come back over here. And the question's about this static method decorator. Recall that in Python, anything that starts with the @ sign is a decorator. And so this decorator is modifying this function. These, let's look at the difference between this function here. Actually, let's go up to the code that I already have written. The balance factor function and the underscore balance factor function. With the balance factor function, notice that the first parameter is called self. And so whenever you use the balance factor function, it will be like your AVL, like the actual object of the tree, dot balance factor with nothing passed in parentheses, that this self is an implicit parameter that automatically gets passed in for you. In these static methods, the difference is that it's sort of attached to the class instead of attached to the instance or attached to the object. It's attached to the class instead of the object. And that means that when you call it, you do, here we go. So here, this is calling the underscore balance factor function, and know that it's not doing self dot underscore balance factor. It's doing AVL tree, the name of the class dot underscore balance factor. Anytime you have a static method, it's always the name of the class dot then the name of the function. So I think the real question though is like, what's the benefit of the static method? And the answer is that you'll notice that inside of the balance factor function here, it doesn't need access to any of the information inside of an instance. I could have rewritten this function as by passing in a self variable like this, and then just not using that self variable anywhere inside of here. And then if I was to use this version, this underscore balance factor with a self and no static method, up here, I would do self dot underscore balance factor. And here I'm only passing in one parameter because the first parameter is the self that's passed in implicitly, and the second one is the node. In terms of runtime, performance, all of those things, it's exactly the same. There's no difference at all. The advantage is just that it sort of tells the programmer, tells other people who are looking at your code that you don't need to have access to this self variable. If I were to see a function like this that is taking self as a parameter, I would expect to find somewhere inside of here the self variable being used. But if you find yourself not using the self variable, then you can just take it out and make it a static method. Inside of the binary tree.py file, we go to the here, these post order print, pre-order, in order print functions You'll notice they're not static methods. They're taking in this self parameter, but they're not actually using that self parameter anywhere. It looks like I'm using it right here when I do self.postorderPrint, but this self is only required because this is not a static method. If I were to convert this to a static method, I could take out this self parameter, and down here I would just put binary tree instead of self, and the code would be a little bit more clear. Yeah, so really the only purpose of the static method is just to annotation to other programmers to make the code a little bit more clear. So I forget who asked that, but did that answer your question somewhere in there?
Yeah.
Any other questions about code so far?
I have a question about how you recommend visualizing our trees as we're working through implementing these functions. I've been relying on Python Tutor, but space is limited on that site. And I started reaching that limit with the previous assignment, and I anticipate this one needing more.
Yeah, it's a great question. So the way when I was implementing my version of this this code, what I relied on anytime I needed to visualize the here it is, the binary tree class. I relied on this node class having this string instance like this, and then the binary tree string instance just calls the node string instance. And again, because the AVL tree will inherit from the binary tree, you'll be able to use this string function to visualize the AVL tree just fine. In order to see exactly what that looks like, go ahead and undo all the changes I've made here. And I'm going to open up the test cases to find an example of a tree, and then we'll visualize that tree. So test/test_avltree.py. And so we have a couple of these AVL trees. I'll go ahead and copy this AVL tree 4 right here. So I did Shift V to enter visual, line mode, Y to yank it. It's like copying it, Shift T to go to the left, opening this window up. And I'm going to paste it, Shift G going to the bottom, P right here to paste this onto my avltree.py right here. Then down here in my terminal, so I need to be in the containers folder, Python 3-I, and import containers.avltree like that, spelled correctly with an E. There we go. And now I can do containers.avltree.avltree4, wrapping it in a string. Let's see. I didn't make it a superclass yet, so it doesn't have access to that string method from before. So I'll go ahead and do that. That's all I have to do. Control D to exit out of Python down here. Let's reload my AVL tree and revisualize this. And this is the sort of the visualization. Yeah, let's see. So I can at this point just look at this and be able to visualize in my head exactly the tree diagrams that I've been drawing on the lecture notes. If you have to take this and go to the lecture or redraw it manually each time, that's okay. But then when I'm working on my functions, so let's say my left rotate function, what I'll do is there'll be maybe 10 lines of code inside of this left rotate function. And we'll have something like line 1 does something, line 2 does something else, line 3 does something else, line 4 does something else. And I'll print out, so here I just typed in node, did my @p macro to be able to print that out. And I want to visualize what the tree is actually going to look like by looking at what the node is going to look like at each one of these steps. And in order to make it a little bit easier about what each of these steps are, I'd add some numbers like this, just so that I don't get confused about looking at the wrong output and matching it up to the wrong spot in the code. And then I can look and see exactly what change did line 1 make to the code, and draw out the tree before and after, make sure that that is exactly what I thought it was going to be. And if things are not working, it'll come to the point where, oh, I realize line 3, the after tree is not what I expected it to be. And so somehow I need to modify what line 3 looks like. Is that along the lines, Jonathan, of what you were asking for?
Yes, thank you.
That was a great question. Any other questions so far? Okay. Maybe, yeah, so there's a couple of good sources to get trees to visualize like this. The main one is from the test cases. You have a bunch of example trees up here of various heights. You want to potentially be able to, like, you know that there's a certain situation that you're trying to get to work, like, oh, maybe you're, so on our cases down here for this rebalance function, maybe all of these ones are working, but it's like this case right here that you specifically need to test. You might have to manually construct a tree to isolate that case, get something that's a good test case for that, and work on that specifically. So don't feel shy about like modifying some of these in your own file. You can't modify the test cases file, but in your AVL tree, create your own tree there to work with. And then again, with these hypothesis library, scroll down a little bit further, all of these test cases for all of the functions, there we go down here, like the insert function and insert list and so on, they're all using this hypothesis library that's going to randomly generate a bunch of integers to insert in here, and then it'll actually output the, when an assert fails, it'll output what the tree is that caused that assert to fail. And so you can copy that into your code over here and just work on that tree, get it to work for a while. And then once you have that working on that test case, then go back and run the PyTest test cases. Let's see. Yeah, so after you get the left and the right rotate working, then the only thing left that has test cases in this class is the insert function. I'm not asking you to do a removal for the AVL tree, and your other operations, find and find min, find max, all of those, you inherit them from the binary search tree, so you don't have to implement them. I do recommend that you implement this underscore rebalance function. Again, it's going to be very similar to the code in the textbook, but there's no test cases for this, so it's just the test cases for the insert function. Let's see, let's go over to the instructions for the homework down here. And the instructions are getting a little bit more complicated. Every week they're getting more and more complicated with the Git tasks that I'm asking you to do. And so this week it's important that your, because the AVL tree is going to inherit from the binary tree and the BST classes, you need to make sure that your AVL tree branch comes off of the BST branch and not off of the master branch, because you need to have access to your implementations of these classes in order for it to work. This part right here is saying that in my AVL tree branch, I've actually not just added the AVL tree and file and test cases, but I've also modified the BST file and test cases. So I'll switch over here to show you what those modifications look like. searching for this function right here, underscore magic function equals. This is a function that was not in your previous assignment in this class, but I've added it now. And so when you do the pull request, you're very likely to get a merge conflict on your bst.py file that you'll have to resolve and make sure that this function gets implemented. The equals magic method just implements the double equal sign comparison operation in Python. And for two trees, we say that they're equal to each other. We don't care about the structure, so we don't care about the left and the right children being the same. What we care about is just that they can't contain the same elements inside of them. And so the easy way to check to see if they contain the same element inside of them is convert them into a sorted list and check those lists for equality. And recall that for any binary search tree, so both a BST and an AVL tree, you can get a sorted list by doing an in-order traversal of the tree. So that'll be the function that you'll want to call to get a sorted list, doing the in-order traversal.
Can I ask a question? What is so I got a merge conflict, and then like you can add and then commit the file, the bst.py, but I'm a little bit confused what the merge conflict is or what it's saying, and if that's the right way to resolve it.
Sure, yeah. So big picture idea of a merge conflict is that when you have a file that's been modified by two different people or two different branches or two different commits, and you try to combine those commits down into the same file. So in this case, this bst.py file has been modified by you in your previous homework assignments. You've implemented all of these other functions, but then it's also been modified by me in my upstream repository. In the AVL tree branch, I added this, this function here without adding any implementations. And so that's the source of this merge conflict, because two different sources modified the same file. What you'll get when this happens is a bunch of lines that look something like there'll be a bunch of equals and one spot, and then a bunch of less thans in another spot, and then greater thans in another spot. And what these represent is the contents of, let's see, so anything that's outside of these weird symbols is the same in both files. And the things that's inside is the things that are different. So what you'll have to do is you'll have to go through and modify it, delete these symbols because they're not valid Python, and just make sure that this equals function appears and that none of your other code gets deleted, because the test cases still rely on your other code being correct as well. Yeah, more detailed explanation than that. If you want like generic explanation, the GitLab has walks through an example merge conflict, and so that would be the place to go for like the theory review of this. But I'm also happy to, like, when you get to this spot in the homework office hours or lab tomorrow, to walk you through the steps of exactly what to do at this point. It'll be a little bit different for every person. Sam, go ahead.
Would you still get a merge conflict if you manually add the new function to your own code?
That's a good question. So the issue of exactly when you get a merge conflict and not get a merge conflict is a fairly complicated one. The actual algorithm that is used in order to determine, so I mean, if you think about it, it's a fairly complicated process to figure out what are the lines that are the same in two files and what are the ones that are different. Sounds like it should be easy, but it's when you sit down and try to write out the code to do that, it's a fairly complicated algorithm. And so depending on the exact details of how you wrote your code before and how you copy and paste it, you may or may not get a merge conflict. So this is one of the things that I think in the instructions, I was very careful when I said you may get a merge conflict. You're not guaranteed to. It depends on a lot of different details. the specific, if you do, so one of the follow-on courses to this course is the graph algorithms course. And in that course, you would talk about the algorithm that actually does these merge conflicts. Did that answer your question, Sam?
Oh, yeah, it did. And I do have a follow-up question. So if you make some changes to your file, and if I make some changes to my file, and if I try to update it to my code, would I still get a merge conflict? And if I do, how would I resolve that? Because there are two different versions that contains a bit that doesn't overlap.
Yeah, that's a good question. So the first part of your question about do you get a merge conflict? You only get a merge conflict when you run one of two commands, either the git merge command or the git pull command. And the reason git pull, what git pull is it's git fetch followed by git merge. So it's really only the git merge command that can cause a merge conflict. And so if you never run git merge, you can't get a merge conflict. In terms of your second question about, and maybe just one other thing on the first part of that is when can you get a merge conflict? So in particular, if you're pushing to your origin repository, pushing never involves merging. And so you're guaranteed never to get a merge conflict when you push up to GitHub. You only get a merge conflict when you pull from my branch or you manually merge from my branch. In terms of like actually resolving the merge conflict, you can actually, in some sense, prove that what Git does is the best automated system for resolving a merge conflict. And beyond what Git does, it's impossible for a computer to figure out. And there is actually no algorithm that can figure it out. And so it requires human manual intervention to go through and look at these annotations and decide, based on your application, what code should stay and what code should go. For every application, that's going to be a different process that's just specific to your particular needs. But in this case, you need to keep all of the code that you had before and keep this new equals function that I'm adding because there are test cases for this function now as well. So great question so far. Any other questions?
So just to clarify,
Yeah, go ahead.
If you add a EQ function, and if I add a EQ-2 function, then would I be able to keep both of them?
So you can keep anything that is a resulting valid Python file is something that you can keep. So if you had EQ and EQ2, that's not going to cause a conflict within Python, and so that would be an okay thing to do. If you had two functions named EQ, from Git's perspective, it doesn't care. Git doesn't look inside the Python at all. It just knows that this is a text file. And so Git would not care if you had two equals functions with the exact same name. But then Python would care when you tried to load it up in Python. Yeah, great questions. Did that answer your question, Sam?
Yeah, it did. Thank you.
Any other questions about anything related to the assignment? Okay, I just want to iterate again that in some sense this is a very simple assignment because it's really only one routine, the insert routine that you're implementing, and the code for the insert is going to be very similar to the code from your BST insert. It'll just be that followed by the rebalance code, which is almost given to you in the book, just with some minor formatting, things that you'll have to change. But don't be deceived by that this is intentionally a relatively small amount of work because it is far and away the hardest work that you'll have to do for this class. So make sure to allocate your time on this assignment appropriately, keeping that in mind. Sam, go ahead.
Can you unmerge?
I'm sorry?
Can you unmerge?
Oh, good question. Questions, can you unmerge two branches that have been merged in Git? And the answer is that this is what's called rewriting your Git history, and is a relatively advanced thing to do in Git. To give you like a sense about the level of advancedness, I use so all the commands that we've gone over in Git so far in class, I use them on a daily, regular basis. Anytime I need to rewrite a Git history, that's probably like a once a year sort of event for me, and not at all something that like have memorized about what the commands are for that. Have to keep the manual open side by side as I'm doing it. So it's possible to do something like an unmerge, but very difficult to, and not in any sense like recommended use of Git, only for very weird situations. The technical name for that is called a rebase in Git. And so you'll hear people talking about rebases a lot, and that's what they're referring to, is anytime you're rewriting the history, you're doing a rebase. One of the things you can do, which is similar to an unmerge, is that in Git you can go back in time. So here I have my, I'm in a Git repository, so I can do git log. Here's all of the previous commits that I've done. And so I could go back in time to any of these commits and check them out. Let's check out my first commit right here, like this. And it's not letting me do it because I have this file right here that I've been typing in changes to up here. So let's go ahead and undo those changes. If you do checkout with the name of a file, it deletes that file and replaces it with whatever is currently in your Git branch or your latest Git commit. So now if I run Git status, you see there's no changes right here. Up here inside of Vim, I'm going to reload this file on Vim with the := command. I have to add the exclamation mark to actually do it, : $! And it reloads those files for me, deleting all the changes that I made. And now if I do my Git checkout with the hash commit like this, it'll take me back in time to this location, ls containers, and you can see that the AVL tree and the BST and such are not there anymore. This is back to Fibonacci and range time period. This git log and traveling backwards in time is something that when you're working with, like on a larger project, collaborating with other people, that you would do on a regular basis. So this is another one of those techniques that's kind of in my back pocket on like a daily basis, use it sort of thing. But here I'm not actually rewriting the history, I'm just traveling through the history. Let's see. So that's our time for today. Happy to stick around and answer more questions, but that's going to be it for class. And I will see you all either on lab tomorrow or next week. And I'll stick around here for office hours for more follow-up questions.
Mike, just a follow-up question to that thing you just shown. Like after we check out the branch, if we want to like make that our main thing, do we use like rebase? Is that what rebase does? Like if we want to make that the most, like the head of the Git.
Oh, okay, this is a good question. So I'll share my screen here in a second. Oh, there it is. Just have to get my terminal windows back and sharing my screen right now. And so down here, I'm currently still at this old commit that's down like this. And the idea is, so wherever I'm at, that's always called head. I'm just bring that up because you use this word head. And in Git terminology, head refers to whatever commit you're currently looking at. If I want to say create a, like actually start working on off of this commit again, then what I do is I create a new branch that points to this commit, doing something like git branch new work like this. And now if I run git branch, you can see that there's this new work branch, and I can do git checkout new work. It's still pointing to the same commit message down here, that in Git, branches are, all that a branch is it's a pointer to a particular commit. And once you're checked out at a branch instead of at a commit, then if I were to add a new commit doing git add something, git commit something else, it'll modify what commit this new work branch points to be whatever the new commit created by my commit is down here. So yes, it's possible to continue working off of one of these older branches, and totally normal and common thing to do. Did that answer your Aaron, your question?
Yep, thank you.